Okay, so our next talk is going to be about mixed testing, specifying and attesting ABI compatibility of C and C++ atomics implementations, and the talk will be given by Luke Geeson.
Thank you. Cool. You can hear me at the back okay? Is that all good? Yep, fantastic. Right. So I'm a PhD student at University College London, and together with my co-authors here, have been finding bugs in C and C++ compilers. So in particular, we're looking for concurrency bugs. I'm just going to get started and give you an example of what that might look like. So look at this example on the left. This is a test we used in a bug we reported in LLVM. It's what we call a litmus test. So it has a fixed initial state where x and y have initial values of 0. And then you have two threads of execution that read and write to these shared x and y variables. And then we have a question over the final state of running this program, which says, is there an outcome of executing these two threads from this fixed initial state where the local variables t and u both have the value 0 at the end? That is the wrong button. According to the C standards, so ISO C or C++, the answer is no. You should not observe that 0,0 outcome. And this is because essentially ISO C has a chapter that specifies the allowed concurrency behavior of these atomic loads and stores. And that gives rise to the semantics of executions, that gives rise to the semantics of these final outcomes. So on the right here, this syntax is quite terse, but that is essentially a set of assignments to T and U. So each one of those is one of the possible outcomes allowed by C or C++. So that's your C program. So when you compile it, you would hope that you don't observe that 0,0 outcome, right? And indeed, if you compile this to target ARMv7, you'll see that the assembly on the left, the pink stuff, is what is generated by LLVM. Now, note here that we have these things called DMBs. They're memory barriers. They prevent the effects of executing the loads or the stores before or after from reordering past this barrier. That, in effect, prevents the reordering, and it also prevents the 0,0 outcome from occurring. So on the right, again, we have these three sets of outcomes, this time using assembly registers as opposed to local variables in C. But again, there's no 0,0 outcome, so we're all good here. The important thing to note here is that the pink sequences are designed to work with the other pink sequences. They work in isolation. Also, if you compile this to target ARMv8, not ARMv7, you get the blue sequences. And in this case, instead of having that DMB fence, we have a STL and LDA instructions. So that's store, release, and load acquire. And the semantics of these are that they pair up together, and they basically form a release acquire barrier, if you will, that prevents the reordering and also prevents that 0,0 outcome once again. So the important thing to note here is that with pink is designed to work with pink, blue is designed to work with blue. However, if you mix them, you observe the 0,0 outcome. And this is a mixing bug. This arises because the store release instruction and the LDR instruction, they don't synchronize. So the LDR does not have ordering semantics with respect to STL. Therefore, one can reorder past the other, giving rise to this 0,0 outcome. This is a mixing bug. This is what we're looking for. This has been reported in LLVM. It's been triaged for fixing by engineers. We haven't fixed it yet. Got a few things to do first, but yeah, that's the kind of thing we're looking for. Concurrency bugs. So to give you a high level, to zoom out a bit and give you sort of the big picture, I guess, we're looking for behaviors of the compiled program under the architectural model or the implementation of the model, so a Raspberry Pi, that are not behaviors of the source program under the source model, which in this case is ISO C or C++. And we're comparing sets of outcomes, which we rewrite so that we can compare machine and source states by using the mappings in the compiler. As we've seen, each atomic operation, so a load or a store, can have one of multiple possible assembly sequences, one of multiple possible implementations. And they can be mixed. This perhaps isn't surprising. This is what linkers have done for years. This is what portable applications are designed to do. But the state of the art hasn't necessarily looked into this all that much. There are a few web pages here, but there's no sort of papers, as it were. So this is what we did, and this is what I'm going to talk to you about today. We have a technique called mixed testing, which allows us to test whether these mappings to different assembly sequences are interoperable. That means they can work with others. And we have a tool called Atomic Mixer that implements this technique. I'll give you an example of some of the bugs we found. And yeah, we're also going to show you briefly a specification that we wrote with my colleagues in ARM's compiler teams to try and prevent some of these bugs from arising in compilers in practice. Because this is a testing paper, we want to provide a spec that we can then implement and test against. Cool. So this is how we found the bug. On the left, we have a fancy LaTeX diagram. What we essentially do is we take a source program S and we split it into its constituent operations. So in this case, I'm going to move now. We take the source program and we split it into its constituent loads and stores. And then we get a set of all the sort of atomic operations you're compiling. And then we apply to those each of the possible mappings. So in this case, the load and the store both have two possible mappings respectively. So in this case, a mapping is defined as you could call it a function from C or C++ atomics to your various assembly sequences. These are typically accessed via like compiler flags. So we compile each of those operations separately. And then we get sets of assembly sequences back for all of the permutations of the compiler under tests. And we combine them into a set C of all the possible combinations of the resultant program. And we show the example of the buggy test earlier. That's just one of the tests that's generated by this sort of this flow, this technique. Cool. So overall, the Atomic Mixer tool essentially implements that whole flow. So splitting, separate compilation, combining. And it takes the test as input and a set of profiles that you're checking, gives you back a set of assembly tests you can then run under some simulation or on hardware to see if you observe reordering bugs. Cool. So we have coined a new term called a mixing bug, which essentially arises when you do this kind of testing. So we call a mixing bug that arises if any of the compiled programs C exhibit a concurrency bug with respect to the source program S. So that's using the concurrency bug definition from before. However, we're going to lean on this a bit because it has a few implications for testing that I think are worth stating up front. The first one is that these bugs only arise when you mix implementations of atomics together. So the prior work essentially takes a whole program, compiles the whole thing using one compiler mapping, and gets one program back. These bugs arise when you mix multiple mappings, and therefore it's sort of strictly more general than the standard testing we've been doing for the last 20 years or so. Precisely, prior work takes one compiler profile and tests the whole program, whereas mixed testing takes multiple compiler profiles and is essentially testing multiple implementations and how they interact. And this unfortunately means that mixed testing is exponential. It's exponential in the number of atomic operations you're testing and the number of compiler profiles you're testing, which means you can't run this every day. You can't deploy this in CI. If LLVM changes 5 times a day, you need to run 10 million tests and do mixing on all of those 5 times a day. It's not feasible. So instead, you might do this when the atomics mappings change in a compiler, which is much less often, but still important. Cool. So that's the technique in the tool and these sort of mixing bugs. To give you an example of how some of these bugs arise, we've given you an overview here as well. So these bugs can arise when you mix together ISA versions like ARMv7 and ARMv8 or ARMv8 and ARMv8.1. And there's a running example there where we mix together ARMv7 and ARMv8 mappings. However, this can apply in other cases too. I should say, we're not mixing, say, like RISC-V and x86 codes. So we put some constraints on what we're actually mixing because it still needs to run on a CPU with a fixed instruction set at the end of the day. So this mixing is allowed, but you have to be careful about how you specify mixing. We also find bugs when you're mixing say, GCC and LLVM implementations together. So one of the bug reports we have open is on atomic structs, where the size and alignment of structs in LLVM and GCC differ, which means one may write or load padding bits where the other one expects data, which means if you mix these together, the program will read nonsense. Some of these bugs have been fixed, some of them are still open. It's all work in progress. But yeah, I encourage you to check out the paper as well, because we've also reproduced sort of non-mixed testing bugs too, just to sort of show how one is a generalization of the other. And we prevented a mixing bug from arising in the JVM when one of ARM's partners asked about whether the mappings would be sound. Again, it wouldn't have arisen in normal circumstances. Cool. So I said mixed testing is exponential. We wrote a specification with our colleagues in the compiler team to try and bound the search base a bit, because yeah, each compiler implements a different set of mappings, and we want them all to be interoperable with respect to each other. So this is essentially 20 pages of the allowed mappings from C atomics down to ARMv8 assembly, in addition to special cases that compilers need to implement. In theory, if your compiler implements this spec and links against the program generated by another ABI compliant compiler, then you shouldn't observe any of these strange reorderings. Up to bounds on test size, of course. So I'm not making any verification or proof claims here. Yeah, I encourage you to check it out. I've also got a copy on my iPad later if anyone wants to have a look. That's about it. That's the technical stuff. Now this is a sort of formal PL testing audience, so some open questions here, like, does this apply to other architectures? This was the reply we got when we reported that atomic struct bug. Someone was asking what the x86 ABI says about all of this, to which the reply was, I've been asking for it to say something for years. So it's possible that this applies to other architectures. We don't know, we haven't looked. And also soundness. So when someone proposes like a C or C++ memory model, they typically provide with it a set of like idealized mappings down to each architecture. This is typically a one-to-one mapping. What we've sort of shown here is that compilers in practice actually have a one-to-many mapping. And so it'd be nice if someone does some multi-mapping soundness proofs. Very clear, easy idea, but probably is a lot of work to actually implement the thing. Cool. So that's the paper. There's an artifact as well if you want to have a look. And that's essentially it. We have a technique that mix tests compilers. We have a tool that implements this. We found some bugs, and we wrote a spec to try and outlaw the scalability problem that comes with mixing all of these implementations. Yeah, one more thing to ask of you. My co-author wrote a really cute little blog post. It's very accessible and easy. If you want an introduction to this kind of relaxed memory concurrency bug finding stuff we've been doing. Provides a bit more context, and also has some cute AI-generated bugs too. Thank you very much. I'm happy to take any questions.
Questions? Yeah, you can just step up to the mic.
Thank you for the talk. Maybe I just want to ask a clarifying question. Like, when you say this mix, you mean a compiler compiles to the binaries with a different target architect, or it's the same architect that you are compiling different part of the program, and then you link them together?
Yeah, so we are taking a program, we're splitting it up, and we're compiling it to target different versions of the same architecture. So ARMv8 and ARMv8.1 are different versions of the ARMv8 architecture. They're compatible, but you couldn't mix those with, say, RISC-V code. That wouldn't make sense.
Oh. So aren't they supposed to be the same instruction set? If it's the same architect with different wording, why is that would be the problem?
So it's the same instruction set, although each architecture version may have slightly different semantics for the same instruction. But it is fundamentally the same instruction set, just with new instructions or slightly different ones. At the end of the day, your program will be compiled, linked together, and it will run on a fixed machine, which will have a fixed semantics.
I see.
But you're going to be mixing a sequence here and a sequence there. The linker might combine them, and then you still may observe reorderings based on what that hardware actually implements from the model.
Okay.
Yeah.
Thanks.
Hi. Great work. Really enjoyed the talk.
Thank you.
These litmus tests are a bit fiddly, right? So if they trigger, clearly you found a bug.
Yep.
If they don't, maybe you missed it. So how do you know when to stop? And were there any litmus tests that are possible but so infrequent that you had to give up and not use them?
Yeah, it's a good question. I gave a CGO talk at the start of this year on addressing this problem, so it's very handy. The state of the art would run this on hardware loads of times, and you're given a high probability of observing bugs, but not guaranteed, right? So what we have here is we're essentially running all of our testing under a simulation of the C model and a simulation of the architecture model. So we're using the official ARMv8 AR64 model, which is encoded into an executable tool, which can essentially give you repeatable results. And they are designed to be reflecting of the ARM architecture reference manual. So they're as close as you can get to a ground truth. That's how we avoid this whole probabilistic problem. That was kind of previous work, and this is kind of the next step. Happy to talk about it later as well.
Follow up if I have time, real quick. How easy is it to use that simulator? Can I, not working at ARM and not being an ARM engineer, use it? Is it that easy? Or
Yeah, there's a GUI for it, the web page.
Oh.
I'll send you a link later. Come and find me.
Please do. I'm working on something similar.
Awesome.
Thank you.
Thank you.
Okay, I had one question.
Sure.
So these are clearly bugs,
Yep.
clearly very nasty bugs. Did you all kind of discover this class of bugs, or is there some bug in the Clang bug tracker involving some horrible war story of someone who couldn't figure out what the heck was going on with their program, and eventually they tracked it down to this kind of bug with a mix of architectures due to some precompiled library, something like that? Do you have any examples of that, or you guys just thought of this?
As far as I can tell, I haven't seen any bug reports like this. I've seen sort of things on mailing lists that allude to problems like this, but I haven't seen someone explicitly write down, this is a mixing problem. This arises because of this. There is like a web page where I believe Peter Sewell tried to list some of the possible mappings that each architecture might have, but no one's really sat down and hashed out the idea, I guess. So I say we coin these things as mixing bugs. They're not necessarily surprising. Again, linkers have been around for a while, but yeah, I guess we're the first ones to write a paper on it. Again, if I'm wrong, I'm happy to be disproven, but yeah, as far as I know, yeah.
Very cool. Okay, let's thank the speaker again.